One, two, 1, 2. 1, 2. All right. Jumping right in. Where are we? Unit testing. Let's go to the quiz. From which class are all Python exceptions derived? Base exception. Which of the following is the correct way to capture a reference to a type error in a variable named e? Accept type error as e. In Python, what is a traceback? Type of error, a class from which exceptions are derived, a summary of an exception included in a program's output, which includes the exception type, a message, and the series of function calls that led to the exception, a control flow. So it's this one. Which of the following classes successfully defines an exception that, when raised, outputs the printer is out of paper? So class out of paper error is an exception. Def string self return the printer is out of paper. This one. Which kind of errors can be handled in Python? Both syntax errors and exceptions can be handled in Python. Only syntax errors can be handled in Python. In Python, only exceptions can be handled. Both. Oh, my fault. What is the output of the following code? So try print 1 plus 2 equals 3, which, okay, it's going to print it. Print 2 plus 3 equals 5. Print 3 plus 4 plus, so this is going to be an error because it's not a 7. And print 4 plus 9, except type error, print a type error occurred. So it's going to try to do this, except if there's a type error, then it's going to do that. And since this isn't a for loop, I think it's just going to get these, yeah. Python executes the try clause until it hits an exception, then it immediately begins executing the except clause. What kind of exception would be raised by the following code? Animal colors equals tiger, orange, viper, red. Print animal colors, panda. It's a key error. What is the output of the following block of code? Try, print, exceptions can be scary. Except, print, although they can also be handled. Else, print, sometimes they can be avoided. Finally, print, coding is fun either way. So it's going to do this, and then it'll do the finally. So wait, accept that. Otherwise, so it does that, then it checks if there's an exception, and if there is an exception, then it does this. If there's not an exception, then it does that. So it's going to be exceptions can be scary. Sometimes they can be avoided. Coding is fun either way. Yeah. What kind of exception will be raised by the following code? A type error. What kind of exception will be raised by the following program? Print undefined variable. So, okay, if it's an undefined variable, then it's going to be a name error. In Python, which keyword is used to throw an exception? To throw an exception, raise. Cool. Introduction to testing. When working with Python or any programming language, there's a lot that can go wrong with our code. There are syntax errors and exceptions, but there are also mistakes in the program logic which cause it to behave in unexpected ways. For these reasons, testing is crucial to creating quality software. The goal of testing isn't just to find bugs, but to find them quickly. Leaving bugs unfound and unresolved can lead to massive consequences in the real world. Take a look at some of the most infamous bugs that have ever occurred in software. Don't worry though, by following some common practices and using the tools built into Python, we can start creating quality tests in no time. To dive in, first, let's talk about the different types of testing styles that exist. The world of testing can generally be divided into two categories. Manual testing. With manual testing, a physical person interacts with software much as a user would. In fact, we have been manually testing our code anytime we run it and observe the results. Automated testing. With automated testing, tests are performed with code. Generally, automated testing is faster and less prone to human error. In this lesson, we'll be diving into the world of testing. For most of the exercises, let's imagine we've been hired to create tests for a new airline company called Small World Air. Before we start writing automated tests, let's do some manual testing and see what kind of shape their software is in. Small World Air provided us access to a program that displays the flight status for all current flights. Manually test the code by running it and observing the output. Traceback most recent call, last file flights.py line 11. print flight plus status must be string, not int. So this flight needs a string conversion. We hit a type error. Can you spot and fix the error? Manually test your bug fix by running the program again. So string flight, and then delete this. Cool. The assert statement. While the previous example was simple to test, most code will be much more complex. It will be very tedious to have to perform these tests manually. Our time would be better spent writing automated tests. Luckily, Python provides an easy way to perform simple tests in our code, the assert statement. An assert statement can be used to test that a condition is met. If the condition evaluates to false, an assertion error is raised with an optional error message. The general syntax looks like this: assert condition, message if condition is not met. Consider the following example that demonstrates the assert statement paired with a function called times10. Note there is a bug in the function for demonstration purposes. So again, hold on, let it sink in. While the previous example was a simple test, most code will be much more complex. Luckily, Python provides an easy way to perform simple tests in our code, the assert statement. An assert statement can be used to test that a condition is met. If the condition evaluates to false, an assertion error is raised with an optional error message. The general syntax looks like this: assert condition, comma, message if condition is not met. So consider the following example that demonstrates the assert statement paired with a function called times10. Note there is a bug in the function for demonstration purposes. Def times10 number, return number times 100. Result equals times 10, 20. Assert result is equal to 200. Expected times 10, 20 to return 200. Instead got plus string result. Here we want to test if our times10 function works as intended. We use the assert statement to evaluate the expression result is equal to 200, since we expect that our function will return 200 given an input of 20. Since this is not the case, this expression evaluates to false. There's a bug in times10, it actually multiplies by 100. We get the following exception: instead got 2000. An assert statement is a quick and powerful way to verify that a program is in the correct state. They can be used to catch mistakes early and make sure we avoid any catastrophes. Let's practice using assert to get a feel for automated testing. Small World Air has a program that runs at the check-in kiosk and asks passengers for their destination airport code. Currently, Small World only flies to 3 destinations: Budapest, Casablanca, and Istanbul. Take some time to examine the program. What should the program return for the current set destination of HND, an airport in Tokyo, Japan? So destinations, BUD, CMN, IST, print welcome to Small World Airlines. What is the airport code of your travel destination? Destination equals HND. Write your code below. City name equals destination's destination. Print great, retrieving information for your flight to city name. So what should the program return for the current set destination of HND? Be a name error, or key error, my fault. This error wasn't a very user-friendly experience. We also want to make sure that users are not entering destinations that Small World Airline does not travel to. Let's add an automated test using assert. Add an assert statement that checks if destination is in the destination's keys. If it isn't, the assertion error message should read, sorry, Small World currently does not fly to this destination. Alright, so write your code below. So city name equals destination. Assert destination. Nice. Unit testing. Assertion statements are a good start to ensuring our programs are being tested, but they don't necessarily tell us what we should test. Generally, we can start by testing the smallest unit of a program. For example, in the real world, if we were testing the functionality of a door, we could test a multitude of units. The handle could be an example of a single unit that we must check to make sure a door functions, followed by the hinges, and maybe even the lock. In programming, these types of individual tests are called unit tests. Like our door handle, we can test a single unit of a program, such as a function, loop, or variable. A unit test validates a single behavior and will make sure all of the units of a program are functioning properly. Let's say we wanted to test a single function, a single unit, To test a single function, we might create several test cases. A test case validates that a specific set of inputs produces an expected output for the unit we are trying to test. Let's examine a test case for our times 10 function from the previous exercise. The unit we want to test, def times 10 number, return number times 10. A unit test function with a single test case. Def test multiply 10 by 0. Assert 10 times 0 is equal to 0. Expected times 10, 0 to return 0. Great. Now we have a simple test case that validates that times 10 is behaving as expected for a valid input of 0. We can improve our testing coverage of this function by adding some more test cases with different inputs. A common approach is to create test cases for specific edge case inputs as well as reasonable ones. Here is an example of testing two extreme inputs. Def test multiply 10 by 1 million. Assert times 10, 1 million is equal to 10 million. Expected times 10, 1 million to return 10 million. Def test multiply 10 by a negative number. Assert times 10, negative 10 is equal to negative 100. Expected times 10, negative 10 to return negative 100. Now we have several test cases for a wide variety of inputs, a large number, a negative number, and 0. We can create as many test cases as we see fit for a single unit, and we should try to test all the unique types of inputs our unit will work with. Now, let's create a variety of unit tests for another feature of Small World Air. At Small World Air, every plane seat has a monitor which displays the nearest emergency exit. This monitor relies on a function called getNearestExit, which takes a row number and then returns an exit location depending on where the row is. Let's make sure our function is working properly by creating a unit test. Create a function called testRow1. That will host a test case. Inside the function, assert that a call of getNearestExit, so one should equal to front. Along with the message, the nearest exit to row 1 is in the front. Create another test case function called testRow20. The nearest exit to row, and assert that the return value is equal to middle. Along with the message, the nearest exit to row 20 is in the middle. Finally, create another test function. Okay. Back. The nearest exit to row 40 is in the back. At the bottom of the file, call each of the 3 test functions we created. What will be the expected output? So the expected output, so if we do 1, location is equal to front, 20, if row number is less, so middle, 40, so we test row 1, assert this, I know that there's going to be an issue with this middle and us doing this back one. Assertion error, the nearest exit to row 40 is in the back. Okay, got you. Since we ran this and it returned middle instead of back, it threw this assertion error. Looks like our test caught a logic error in our function, getNearestExit. If the row number is larger than 30, we actually want to return back. Adjust the function and fix the error so all of our tests pass. We should see no output. Python's unit test framework. There are some problems with the approach to our previous unit tests that would make them difficult to maintain. First, we had to call each function specifically when a new test was created. We also didn't have any way of grouping tests, which is necessary when the number of tests increases. Perhaps most importantly, if one test failed, the assertion error would prevent any remaining tests from running. Luckily, Python provides a framework that solves these problems and provides many other tools for writing unit tests. This framework lives in the unit test module, which is included in the standard library. It can be imported like so. Import unit test, the rest of our program. The unit test module provides us with a test runner. A test runner is a component that collects and executes tests and then provides results to the user. The framework also provides many other tools for test grouping, setup, teardown, skipping, and other features that we'll soon learn about. First, let's refactor our test for the times 10 function to use the unit test framework. There are several things we need to do. First, we must create a class which inherits from unittest.testCase as follows. Import unit test, class, test times 10, unittest.testCase pass. This class will serve as the main storage of all our unit testing functions. Once we have the class, we need to change our test functions so that they are methods of the class. The unit test module requires that test functions begin with the word test, so our existing names work well. Import unit test, class, test times 10, unittest.testCase, def test multiply 10 by 0, self, pass, and 1 million in negative number, all taken self and pass. Lastly, we need to change our assert statements to use the assert equal method of unittest.testCase. The framework requires that we use special methods instead of standard assert statements. Don't worry, we'll cover these methods in the remainder of this lesson. For now, simply get used to the syntax. Here's what our class looks like after the change. So import unit test, class, test times 10, unittest.testCase, def test multiply 10 by 0, self.assert equal, times 10, 0, 0, expected times 10, 0 to return 0. Okay, so the syntax is you import unit test, you define a class, and you pass it unittest.testCase, and then within that class you define function like test functions. You pass it self, and in it you do self.assert equal, and its first argument is the function you want to test, and pass it the thing you want to pass it, and then comma the thing you're passing it, or sorry, the answer you expect, and then comma the reply to return if it doesn't return the value you expect. So for def test multiply 10 by 1 million, self.assert equal, times 10, 1 million, comma 10 million, comma expected times 10, 1 million to return 10 million. That's it. Now we can run our test by calling unittest.main. The unit test framework will work its magic to detect any tests in the existing module, run them, and provide us results. Our final code would look like this. So importing unit test framework, import unit test, function that gets tested, def times 10 number, return number times 100, test class, test times 10, unittest.testCase, def test multiply 10 by 0, self.assert equal, times 10, 0, 0, expected times 10, 0 to return 0, def test multiply 10 by 1 million, self.assert equal, times 10, 1 million, 10 million, expected times 10, 1 million to return 10 million, def test multiply 10 by negative number, self.assert equal, times 10, negative 10, negative 100, expected add times 10, negative 100, negative 10 to return negative 100, run the test, unittest.main. When we run this code, we would see the following output: fail, this trace back, the negative 1, fail, the 10 million one. In the test output, we can see that 2 of the tests failed, test multiply 10 by 1 million, and test multiply 10 by negative number. Let's get some practice with the unit test by refactoring our previous test cases for small world air, and then we will dive into learning all the useful testing methods we can work with. First, let's import unit test at the top of the file. Next, after the getNearestExit function, create a class called nearestExit. Should inherit from unittest.testCase. refactor test row 1. Okay. Oh wait, refactor them so that they are methods of this class. Don't forget to add the self argument. Okay. So self.assert equal get nearest exit 1 front, and the nearest exit to row 1 is in the front. And self.assert equal get nearest exit 20 middle, the nearest exit to row 20 is in the middle. Self.assert equal get nearest exit 40 back, the nearest exit to row 40 is in the back. Change the assert statements in these functions so that they instead call the self.assert equal method with the correct arguments. Remove the 3 function calls from the bottom of the file. Replace them with a single call to unit test.main. Looks like it's the same bug from before. So fail test row 40, main nearest exit test, traceback most recent call last, file exits.py line 23. In test row 40, self.assert equal get nearest exit 40 back, the nearest exit to row 40 is in the back. Assertion error middle not equal to back, middle, back, the nearest exit to row 40 is in the back. Run 3 tests in 0 seconds, failures equals 1. Looks like it's the same bug from before. Fix the error in the get nearest exit function. We should no longer get any failed tests when we run our script. Run 3 tests in 0 seconds. Okay. Assertion methods 1, equality and membership. In the last exercise, we saw how to check for equality between 2 values in the unit test framework using the .assert equal method of the test case class. The framework relies on built-in assert methods instead of assert statements to track results without actually raising any exceptions. Specific assert methods take arguments instead of a condition, and like assert statements, they can take an optional message argument. Let's go over 3 commonly used assert methods for testing equality and membership, their general syntax, and their assert statement equivalents. Assert equal. The assert equal method takes 2 values as arguments and checks that they are equal. If they are not, the test fails. So self.assert equal, value 1, value 2. Assert in. The assert in method takes 2 arguments. It checks that the first argument is found in the second argument, which should be a container. If it is not found in the container, the test fails. Assert true. The assert true method takes a single argument and checks that the argument evaluates to true. If it does not evaluate to true, the test fails. Self.assert true, value. The equivalent assert statements would be the following. Method self.assert equal to 5, equivalent assert 2 is equal to 5. Self.assert in 5, 1, 2, 3, assert 5 in 1, 2, 3. Self.assert true, equivalent assert bool 0 is true. Okay. Small world airplanes are equipped with an onboard entertainment system which we need to create some tests for. Take some time to review entertainment.py and test.py. Note the 3 functions in entertainment.py. So if we come to entertainment.py, def get daily movie, print retrieving the movie set to play on today's flight, return Parasite, def get licensed movies, print retrieving the list of licensed movies from the database, licensed movies equals Parasite, Nomadland, Roma, return licensed movies, def get Wi-Fi status, print checking Wi-Fi signal, print Wi-Fi is inactive, return false. And import unit test, import entertainment, write your code below, class entertainment system test, unit test.test case, def test movie license, self, daily movie, assign entertainment.get daily movie to daily movie, entertainment.get daily get licensed movies, assign that to licensed movies, Dev test Wi-Fi status self. Entertainment.get Wi-Fi status to Wi-Fi enabled unit test.main. So note the three functions in entertainment pie. So return movie of the day. Get licensed movies returns a list of licensed movies the plane can play. Get Wi-Fi status returns the current Wi-Fi status of the plane. Note the two test cases in test.py. Test movie license is intended to test if a daily movie is licensed. Test Wi-Fi status is intended to test if the Wi-Fi is currently active. Run the code to proceed. Retrieving the movie set to plan today's flight. Wi-Fi is active. Okay. Every flight has a free movie. We want to create a test that checks our database to make sure that the uploaded movie has a valid license, or else we could pay some hefty fines. Inside of our test movie license test method, we have two variables defined. Daily movie, which stores the value of the current free daily movie. Licensed movies, which stores the value of all the current licensed movies. To test if we have a license for the current daily movie, we need to compare if daily movie exists inside of licensed movies. Use the self.assert method inside of test movie license to check if the daily movie is licensed. So we can do self.assert in daily movie licensed movies. Our entertainment system also provides Wi-Fi as a purchase option for passengers. We want a test that ensures the Wi-Fi is enabled. Inside the test method called test Wi-Fi status, we have a variable called Wi-Fi enabled, which stores the Boolean value of whether the Wi-Fi is turned on or not. Use the self.assert true assert method inside of test Wi-Fi status to test that Wi-Fi enabled is true. The test should fail because currently Wi-Fi is disabled. So self.assert true Wi-Fi enabled, and it fails. Assert methods 2, quantitative methods. Often we need to test conditions related to numbers. The unit test module provides a handful of assert methods to achieve this. Let's take a look at two common assert methods related to quantitative comparisons, their general syntax as well as their assert statement equivalents. Assert less. The assert less method takes two arguments and checks that the first argument is less than the second one. If it is not, the test will fail. Self.assert less, value 1, value 2. And assert almost equal. The assert almost equal method takes two arguments and checks that their difference, when rounded to 7 decimal places, is 0. In other words, if they are almost equal, if the values are not close enough to equality, the test will fail. Self.assert almost equal, value 1, value 2. Checks their difference when rounded to 7 decimal places is 0. Okay. The equivalent assert statements would be the following. Self.assert less, 2, 5, would be assert 2 is less than 5. Self.assert almost equal, 0.22, 0.225. Assert round, 0.22 minus 0.225, 7 is equal to 0. Our entertainment.py file has a function called get maximum display brightness. Calculating maximum display brightness in nits, return 3.99 point a bunch of nines. And so that returns the max screen brightness value. Create a test method called test maximum display brightness. And store the return value in a variable called brightness. Next call. Oh. Goodness. Assert almost equal. To make sure that brightness is almost equal to 400. So brightness and 400. It failed. What did I do wrong? Bright. Assert almost equal. Value 1 is brightness. Test maximum display brightness. Takes 0 positional arguments, but was given 1. Oh. Our entertainment.py file has a method called entertainment.getDeviceTemp that returns the current device temperature. Create a test method called testDeviceTemperature. Inside the method, do the following. So call entertainment.getDeviceTemp and store the return value in a variable called deviceTemp. Then call self.assertLess to make sure that device temp is less than 35. The test should fail because the current temperature is 40. Cool. Assert methods 3, exception and warning methods. There is another group of assert methods related to exceptions and warnings. Note that while we haven't covered warnings in detail yet, they are a type of exception. Let's go over 2 of these methods and their general syntax. Assert raises. The assert raises method takes an exception type as its first argument, a function reference as its second, and an arbitrary number of arguments as the rest. It calls the function and checks if an exception is raised as a result. The test passes if an exception is raised. Focus. Exception and warning methods. There is another group of assert methods related to exceptions and warnings. Note that while we haven't covered warnings in detail yet, they are a type of exception. Let's go over 2 of these methods and their general syntax. Assert raises. The assert raises method takes an exception type as its first argument, a function reference as its second, and an arbitrary number of arguments as the rest. It calls the function and checks if an exception is raised as a result. The test passes if an exception is raised, if an exception is raised, is an error if another exception is raised, or fails if no exception is raised. This method can be used with custom exceptions as well. Self.assert raises, specific exception, function arguments. Assert warns. The assert warns method takes a warning type as its first argument, a function reference as its second, and an arbitrary number of arguments for the rest. It calls the function and checks that the warning occurs. The test passes if a warning is triggered and fails if it isn't. So self.assert warns, specific warning exception, function arguments. There are no particular concise ways to replicate these tests using the assert keyword, so it is recommended to use these methods instead when possible. The full list of exception and warning methods can be seen in the... we need to create some tests for the airplane alert system so that the flight crew is properly notified of critical events. Let's start by creating a class called system alert tests, which inherits from unit test.testCase. So class system alert tests unit test.testCase. We're going to create a test for any power outages that might occur on the airplane. Check out the custom exception power error and our function that raises the error power outage detected in the alerts.py file. So import warnings, class power error, exception, pass, class water level warning, pass, def power outage detected. If outage detected, raise power error. A power outage has been detected somewhere in the system. Else print all systems receiving power. Def water levels check, liters. If liters is less than 200, warnings.warn, water levels has fallen below 200 liters, water level warning, else print water levels are adequate. So we're going to create a test for any power outages that might occur on the airplane. Check out the custom exception power error and our function that raises the error. Power outage detected. If outage detected, raise power error. In the alerts py file, the file is already imported into test py for us. In our system's alert test class, create a test method called test power outage alert. So def test power outage alert self. Inside the new method, use self.assert raises to check that an alerts.power error is raised whenever alerts.power outage detected is called with an argument of true. So the test should pass since we are passing a value of true and the exception is raised. We are going to create a test for any water level warnings that occur on the airplane. Check out the custom exception water level warning and our function that raises the warning water levels check in the alerts.py file. So water level warning, water levels check liters. If liters is less than 200, warnings.warn, water levels have fallen below 200 liters, water level warning, else print water levels are adequate. Inside the new method, in our systems alert test class, create a test method called test water levels warning self. Use self.assert warns alerts dot water level warning alerts dot water levels check to check that an alert's water level warning is raised whenever water levels check is called with an argument of 150. This test should pass since we are passing a value less than 200. Parameterizing tests. In previous examples, we created test cases for the times 10 function with various inputs. However, the actual logic of our test really didn't change. To decrease repetition, Python provides us a specific toolset for tests with only minor differences. This is known as test parameterization. By parameterizing tests, we can leverage the functionality of a single test to get a large amount of coverage of different inputs. To accomplish test parameterization, the unit test framework provides us with the subtest context manager. Let's refactor our previous test class to utilize it and see it in action. Import unit test, the function we want to test, def times 10 number, return number times 100. Our test class test times 10, unit test.testCase, a test method, def test times 10 self, for num in 0, 1 million, -10, with self.subtest, expected result equals num times 10, message equals expected times 10 plus string num, to return plus string expected result, self.assert equal times 10 num, expected result message. Here in our test method, test times 10, instead of writing individual test cases for each input of 0, 10, and 1 million, we can test a collection of inputs by using a loop followed by a with statement in our subtest context manager. By using subtest, each iteration of our loop is treated as an individual test. Python will run the code inside of the context manager on each iteration. If one fails, it will return the failure as a separate test case failure. Just like before, We're using the assert equal method to check the expected result, and we are expecting, due to an error in times 10, that the cases of using an input of -10 and 1 million will fail. Here is the new output. Fail. Test times 10, main test times 10. Trace back this, assertion error. This is not equal to this. Expected this to return this. Fail this. Trace back most recent call last. File scratch.py line 12 in this. Self.assert equal times 10 num. Expected result message assertion equals -1000. It's not equal to -100. Expected times 10, -10 to return -100. If we want to expand our test coverage, we can simply modify the list that our loop iterates over. We can test a range of thousands of inputs simply by using the context manager setup to achieve test parameterization. Optionally, we can give our subtest better readability by making a small change in our code for the first argument of self.subtest. The below code has most of our script omitted for brevity, but uses the same script we executed above. More code above for num in 0, 1 million, -10 with self.subtest num, more code below. This makes our test clearer because our test error message goes from fail test times 10 main test times 10 subtest to fail test times 10 main test times 10 1 million. When working with large amounts of test inputs, it is much easier to distinguish which case failed. We can actually use any message we want as the first argument, but using the tested case is usually the best way to increase readability for ourselves and other developers. By using test parameterization, we made our code base much cleaner and more maintainable. Let's get some practice by refactoring some of our previous tests. Small World Air is growing and has added many more movie options to the entertainment system. We can see them inside of entertainment.py. Let's adjust our entertainment system tests class to make sure they all get tested. Replace the call to entertainment.getDailyMovie with entertainment.getDailyMovies, our new method. Lastly, for better readability, update the variable name DailyMovie to DailyMovies. After updating this variable name, update the first argument in the call to self.assertin to use this new variable name. So, entertainment systems tests, replace the call to entertainment.getDailyMovie with getDailyMovies. Lastly, for better readability, update the variable name DailyMovie to DailyMovies. After updating this variable name, update the first argument in the call to self.assertin to use this new variable name. Under our two variables, write a for loop that iterates over DailyMovies. So and stores each iteration value into a variable called movie. For movies and DailyMovies, movie equals movie. For now, let's simply print movie on each iteration. Looks like you have an error. Double check your syntax. So for movies in DailyMovies, movie equals movies, print movie. You create a for loop which iterates over each movie in DailyMovies. So for movie in DailyMovies, I guess that's what it wants. Indent our self.assertin call to be inside the for loop. And change the first argument in self.assertin from DailyMovies to movie to represent the individual movies on each iteration of the loop. Note, creating this structure might be okay at first glance. It may even make you wonder why we need the context manager. But if we run our test, we will see that the test will fail in the middle of our movies collection and won't check the rest. It stops at Black Widow and not Spiral. This is because, like many testing frameworks, unit tests will fail and stop on the first failure it encounters. Lastly, under our print statement of movie, but before our assertin call, insert a self.subtest. To wrap our test method. To make sure we can distinguish test cases between each movie, pass a single argument of movie into self.subtest. Don't forget to preface the context manager with a with statement and indent our self.assertin statement. Now we can observe testing multiple movies and if they are licensed or not. So it would be for movie in DailyMovies, print the movie with self.subtest movie, self.assert in movie license movies. So for a loop, print statement with statement using, oh, I forgot the colon. This statement using subtest, assert in test case. So it goes through all of these and tells us which one failed. Test fixtures. One of the most important principles of testing is that tests need to occur in a known state. If the conditions in which a test runs are not controlled, then our results could contain false negatives, invalid failed results, or false positives, invalid passed results. This is where test fixtures come in. A test fixture is a mechanism for ensuring proper test setup, putting tests into a known state, and test teardown, restoring the state prior to the test running. Test fixtures guarantee that our tests are running in predictable conditions, and thus the results are reliable. Let's say we are testing a Bluetooth device. The device's Bluetooth module can sometimes fail. When this happens, the device needs to be power cycled, shut off and then on, to restore Bluetooth functionality. We would not want tests to run if the device was already in a failed state, because these results would not be valid. Furthermore, if our test caused the Bluetooth module to fail, we want to restore it to a working state after the test run. So we add a test fixture to power cycle the device before and after each test. Here's how we might do it. Def power cycle device, print power cycling Bluetooth device, class Bluetooth device test, unit test.test case, def setup self, power cycle device, def test feature A, self, print testing feature A, def test feature B, self, print testing feature B, def teardown self, power cycle device. The unit test framework automatically identifies setup and teardown methods based on their names. A method named setup runs before each test case in the class. Similarly, a method named teardown gets called after each test case. Now, we can guarantee that our Bluetooth module is in a working state before and after every test. Here's the output when these tests are run. Power cycling Bluetooth device, testing feature A, power cycling Bluetooth device, blah, blah, blah. Okay, ran 2 tests in 0 seconds. Let's consider another scenario. Perhaps our tests rely on working Bluetooth, but there is nothing in the test that would cause the Bluetooth to stop working. In this case, it would be inefficient to power cycle the device before and after every test. Let's refactor the previous example so that setup and teardown only happen once, before and after all tests in the class are run. So def power cycle device, print power cycling device Bluetooth, power cycling Bluetooth device, class Bluetooth device test, unit test.test case, class method, def setup class, CLS, power cycle device, def test feature A, self, print testing feature A, def test feature B, self, print testing feature B, at class method, def teardown class, power cycle device. We replaced our setup method with the setup class method and added the class method decorator. We changed the argument from self to CLS because this is a class method. Similarly, we replaced the teardown method with the teardown class method. Now we get the following output. Power cycling Bluetooth device, testing feature A, testing feature B, power cycling Bluetooth device, ran 2 tests in 0.00 seconds. Okay. In addition to calling functions, we can also use setup methods to instantiate objects and or gather any other data needed. Anything stored in our class will be available throughout our test functions. It's generally good practice to create fixtures that run for every test. However, when a fixture has a large cost, i.e. it takes a long time, then it might make more sense to have it run once per test class rather than once per test. Let's practice setting up text fixtures. In our test.py file, we have some simple tests written for the passenger check-in experience at the kiosk for Small World Air. We also have some functions we are testing written in kiosk.py. Take some time to review the provided code in both files. Run the code to continue. So import unit test, import kiosk, class check in kiosk tests, unit test.test case, def test check in with flight number self, print testing the check-in process based on flight number, def test check in with passport self, print testing the check-in process based on passport, write your code below unit test.main, def power on kiosk, print powering on the check-in kiosk, def return to welcome page, print returning check-in kiosk to welcome page, def power off kiosk, print powering off the check-in kiosk. We want to make sure the kiosk is powered on before we run any tests. This is a great time to set up some test fixtures. Create a setup class method, which takes a single argument CLS and calls kiosk.power on kiosk. Add the add class method decorator on top of it. Class method kiosk.power on kiosk. We don't want to leave the kiosk powered on after all the tests. So powered on the check-in kiosk, testing the check-in process based on flight number, testing the check-in process based on passport, ran 2 tests. We don't want to leave the kiosk powered on after all tests are run. Create a teardown class method. Which takes a single argument CLS and calls kiosk.power off kiosk. Add the class method decorator on top of it. We also want to make sure that customers are on the welcome page before each test runs. Create a method called setup inside of the method. So inside of the method, call kiosk.return to welcome page and welcome page. Oops. That's what I get for not paying full attention because I'm stressed. To create a method called setup that takes a single argument called self, which calls kiosk.return to welcome page. Oh, I forgot to call it. Great. We're good. Skipping tests. Sometimes we have tests that should only run in a particular context. For example, we might have a group of tests that only runs on the Windows operating system, but not on Linux or Mac OS. For these situations, it's helpful to be able to skip tests. The unit test framework provides 2 different ways to skip tests: the @unit_test skip decorator, the skip test method. First, let's examine the skip decorator option. There are 2 decorator options to accomplish the goal of skipping a test. Let's observe both of them in the example below. Import sys class Linux tests unit test.testcase @unittest.skip unless sys.platform.starts with Linux. This test only runs on Linux. Def test Linux feature self print this test should only run on Linux. Unit test.skip if not sys.platform.starts with Linux. Test this test only runs on Linux. Def test other Linux features self print this test should only run on Linux. Let's break down both skip decorator options. The skip unless option skips the test if the condition evaluates to false. The skip if option skips the test if the condition evaluates to true. Both share common requirements. Firstly, both of the skip decorators are prefaced with @unittest to denote the decorator pattern. They both take a condition as a first argument, followed by a string message as the second. In this example, both decorators achieve the same goal, skipping the test if the operating system is not Linux. If we ran the tests on a Mac OS system, we would get the following output. Ran 2 tests in 0 seconds. Okay, skipped 2. The second way to skip tests is to call the skip test method of the test case class, as in this example. Import sys class Linux tests unit test.testcase def test Linux feature self. If not, sys.platform.starts with Linux. Self.skip test only runs on Linux. Here we call self.skip test from within the test function itself. It takes a single string message as its argument and always causes the test to be skipped when called. When run on Mac OS, we get the following output. S ran 1 test in 0 seconds. Okay, skipped equals 1. Skip decorators are slightly more convenient and make it easy to see under what conditions the test is skipped. When the conditions for skipping a test are too complicated to pass into a skip decorator, the skip test method is the recommended alternative. Let's practice skipping tests in our Small World Air application. Small World Air continues to grow. They recently added some regional jets for shorter flights. Unfortunately, these planes don't have an onboard entertainment system. Let's modify our entertainment system tests to make sure these tests get skipped on regional jets. Use the @unittest.skipIf decorator to test movie license. So, test movie license. Let's modify our entertainment system test to make sure these tests get skipped on regional jets. @unittest skip if decorator to test movie license. It should skip the test if entertainment.regionaljet returns true. The message should output not available on regional jets. Okay, full honesty, I don't have time for this right now. So I'm just gonna have to pick back up. Okay, wait. Trying to finish a call. You should skip the test of entertainment.regionaljet. Hold on, let me just check the traffic right now. Okay, we can do this. Small World Air continues to grow. They recently added some regional jets for shorter flights. Unfortunately, these planes don't have an onboard entertainment system. They use the unit test skip if decorator to test movie license. And skip. So skip if not skip if this and that. Add the unit test skip unless decorator to test Wi-Fi status. It should skip the test unless entertainment.regionaljet returns false. So skip unless not this. The message should be not available on regional jets. Unit test skip unless takes two arguments. The first is a condition, can be the result of a function call. If the condition is false, the test is skipped. Oh, is false. Whoops. What else did I do wrong? Expected failure. Sometimes we have a test that we know will fail. This could happen when a feature has a known bug or is designed to fail on purpose. In this case, we wouldn't want an expected failure to cloud our test results. Rather than simply skipping the test, unit test provides a way to mark tests as expected failures. Expected failures are counted as passed in our test results. If the test passes when we expected it to fail, then it is marked as failed in test results. Set up a test to have an expected failure. Okay, this is all well and good. I really have to go. So